Hello. All right, let us consider problem 5. So in problem 5, we have a game with two players, player 1 choosing between T and B, player 2 choosing between left and right. So what we want to do, as we do, is we want to find first the pure strategy Nash Equilibria of this game, and then we want to find the mixed strategy Nash Equilibria. So two objectives. So let's start with part A. We want to go through, kind of like we did in problem 4, and just identify what strategies are best responses for each player, given an action of the opponent. So let's start with player 1. So I'll just write, P1, P2, just to be clear. Who is who? The payoffs for player 1 are on the left, payoffs for player 2 are on the right. Okay, so player 1, given that player 2 is playing L, and we're in this column, we can see that player 1's best response is to play T, because they get payoff of 2 versus a payoff of 1. So we see that their best response is to play 2. Their best response is to play T. Okay, now suppose player 2 is playing R. Here we see that they would prefer to play B. Player 1 would prefer to play B because they get a payoff of 3 versus a payoff of 0. So these are the best responses for player 1. Now let's do the same thing and look at the best responses for player 2. Suppose first that player 1 is playing T. What's the best response for player 2? Well, they could get 1 if they play L, and they get 0 if they play R. So they're going to prefer to play L. That's their best response. Finally, let's say player 1 plays B. What's the best response of player 2? Well, they get 2 from playing R and 1 from playing L. So they're going to play R. That's their best response. Okay, we've gone through, found best responses. Now we want to find simultaneous best responses. So looking at this, it's there are only 2 cells that have 2 underlines. This indicates that both of the players are best responding to the action of the other player. This indicates that both of these are Nash Equilibria. Okay, so these are the 2 pure strategy Nash Equilibria of this game. So I'm going to denote this again as PSNE. Sorry, my pencil's being a bit funky. PSNE is equal to the 2 combinations of actions that are equilibriums. So T, comma L, and B, comma R. So these are the 2 Nash Equilibria for this game in pure strategies, right? So when I say pure strategy, it just means one player's picking one action, the other's picking another action. They're not mixing. But don't worry, we will do the mixed strategy Nash right about now. So if you've been holding your breath, and you really wanted to do the mixed strategy Nash, well, you are in luck, because that's exactly what we're going to do. So I'm going to take a little selection of this and just bring it down below so that we can reference it without having to without having to keep scrolling up and down. So I forgot how to do this. I'm going to do this. Do this and then crop it. Okay. Work smarter, not harder. Well, not really smarter, just avoid working harder. Sorry for the delays. Okay, perfect. Sorry about that. So what we want to do is we want to find the mixed strategy equilibria for this game. So what I'm going to do is I'm going to assume that player 1 is playing L with probability P, and R with probability 1 minus P. Sorry, this is player 2. This is player 2 up here, and I'll use this color for player 1. So player 1 is playing T with probability Q, and B with probability 1 minus Q. So these, again, are the probabilities that each player plays a given action. So P is the probability that player 2 plays L, and the probability they play R is 1 minus P. Similarly, Q is the probability that player 1 plays T, and 1 minus Q is the probability that player 1 plays B. Okay, so what we want when we're finding a mixed strategy equilibrium, we want to have the utility of player 1 from playing L, sorry, not L, from playing T, given the strategy Q, P, 1 minus P. So this is just one way of writing it. This is the utility of player 1 from playing T, given the mixed strategy P, 1 minus P, by player 2. We want this to equal player 1's expected utility from playing B, given the same mixed strategy chosen by player 2. So in other words, we need player 1 to be indifferent between their two actions. Okay, so this is what we would need. Because remember, when we're finding a mixed strategy Nash, we want to find probabilities so that each player is making the other player indifferent, so they get the same expected utility from either of their actions. If both players are doing this, then it makes it so that neither player has a profitable deviation away from this strategy. So this is going to be an equilibrium of this game, when players are both randomizing. So what we're going to first want to do is find a probability P, and 1 minus P, so that player 1 is indifferent between their actions. So what we do is we first have to find the expected the expected utility of playing T, and the expected utility of playing B, given this randomization chosen by player 2. So we can go through and find that the utility of player 1 from playing T, given mixed strategy P, 1 minus P, is equal to P times player 1's payoff at this point, which is 2. So it is 2 times P plus 1 minus P times the payoff when player 1 plays T and player 2 plays R, which is 0, plus 1 minus P times 0. So this is just equal to 2P. Similarly, we can find that the utility of player 1 playing B, given the same mixed strategy, this is equal to 1 times the probability we're in this column, which is P, plus 3 times the probability we're here, which is 1 minus P. So it's going to be 1 times P plus 3 times 1 minus P. So I'm going to simplify this. This is just 1 plus 3 minus 3P, which is equal to, this is not 1. This is a P plus 3 minus 3P. So it is 3 minus 2P. Okay. So to set these equal to each other, I'm just gonna, So if these are equal, we would need 2P to equal 3 minus 2P. So this means that we would need 4P is equal to 3. In other words, we need P is equal to 3/4. So what we did was we found the probability for player 2 to play to play L, and they'll play R with probability 1 minus P. This will make player 1 indifferent between playing T and B. So again, just to summarize, player 1 is indifferent between playing T and B, given that player 2 plays L with probability P and R with probability 1 minus P, where P is equal to 3/4. All right. So that's a way of representing with words what we mean. So now we want to do the same thing, but for player 2. So now we need the utility of player 2 from playing L, given that player 1 is playing T with probability Q and B with probability 1 minus Q. We need this to equal the utility of player 2 playing R, given the same mixed strategy. All right, I'm going to copy this again just so that we can kind of zoom in. Okay. So we first need to compute these two things. So let's first compute the utility of player 2 from playing L, given mixed strategy Q1 minus Q, played by player 1. So this is equal to, here we see player 2 gets 1 when they play L, and player 1 plays T. This occurs with the probability Q, meaning that they get Q times 1 plus, so player 1's playing L, player 2 is playing L, and then player 1 plays B with probability 1 minus Q. This means that they get payoff of 1, and then this is weighted by the probability 1 minus Q. So it's 1 times 1 minus Q. We simplify this. This is just Q plus 1 minus Q. So this is equal to 1. Similarly, for the expected utility of player 2 from playing R, given mixed strategy Q 1 minus Q, this is equal to, it's 0 with probability Q. So it's 0 times Q plus 2 times probability 1 minus Q. So this is going to be 2 times 1 minus Q. All right. And this is equal to 2 minus 2Q. Okay. So in order to have the utility of player 2 from playing L equal to their utility from playing R, we can just set these equal to each other, and we want to solve for Q. So we note that this indifference happens only when we have 1 is equal to 2 minus 2Q. So if we rearrange this and solve for Q, we get 2Q is equal to 1. So this would require that Q is equal to 1/2. So this means that when, so just to kind of box this in, this means that player 2 is indifferent between playing L and R when player 1 plays T with prob 1/2 and B with prob 1/2. Okay. So these are our two conditions for the mixed strategy Nash equilibrium. So if I draw a fun little arrow down from both of these, what color? Let's use that. Okay. So the mixed strategy Nash equilibrium is going to consist of the following. So we need player 1 to play T with probability 1/2 and B with probability 1/2. So what I'll do is I'll indicate this. So I'll say this is P1. So indicating player 1, and this is Q, or it's the probability, sorry, my pen's acting up, P of player 1's choosing between T and B, so this is the P of T, this is the probability of B. And then here, for player 2, player T2 needs to play L with probability 3/4 and R with probability 1/4. So we can translate that here. We would just have 3/4 as the probability of L, and 1/4 as the probability of R. So this is player 2's mixed strategy. Okay, so just to recap, we found a set of probabilities for each player, so which make the other player indifferent between choosing any of their actions. So player 2 plays player 1 plays T and B with equal probability, and this makes player 2 indifferent. Similarly, player 2 plays L with probability 3/4 and R with probability 1/4, and this makes player 1 indifferent between any of their actions. When these both simultaneously hold, it means that both players are indifferent between any of the actions that they have available to them. This means that randomizing is one of their best responses, and thus this is an equilibrium. Neither player has a strict incentive to deviate from this because they're indifferent between all of their actions. They can't improve by picking L or picking R or T or B. Their best response is to stay here. All right.